So today we're going to be talking about streams. So to explain why we care about streams, just a second here. Come on. Let's look at a simple algorithm here. So here I want to count, I have a list of words, and I want to count how many of these words are longer than 10. So here I have a counter. I now go through the words. If I find one that's longer than 10, I increment the counter. And now you'd say, what's wrong with that? That's what we've been doing for as long as humans walked the earth. But there is actually a better way. In the Java Stream library, what you do is you make yourself this data structure called a stream, and we'll talk in great detail what that means. So instead of having a list of words, we'll have this stream of words. And then we're telling the stream, hey, you stream, go ahead and filter only those words that are at least 10 characters long, and then count them. And so clearly it's simpler because you didn't have to keep an explicit counter, and you didn't have to worry that this data structure was traversed linearly from the beginning to the end. So both the policy of how the traversal went and the exact implementation of the algorithm was something that was hidden from you. So you tell the stream what you want, and you leave it to the stream to figure out how you want it. Now you might say, well, what can the stream do with that information? Can it do any better than what I could do by hand? And indeed it can. If we tell the stream that we would like it to use as many cores as your machine has to work in parallel, then in fact the stream will automatically, without you having to do anything, run these operations in parallel. In other words, what it will do is it'll take your data structure, chop it up into little pieces, and have core number 1 work on one part, core number 2 work on another part, and so on, so that you get the same result, just faster. Alternatively, who says that all of that information had to be on a single processor? I mean, we're now in 2015, and where is your information? It's somewhere in the cloud, right? And so there may be something here, and something there, and something there. And then again, the stream can have that knowledge, and it can tell one of the processors that's far away to do a local computation, another one to do another local computation, and unify the results. The programmer doesn't have to know. The programmer can use the same data structure. Now, you've of course seen something like that before. When you used SQL and you query a database, you tell the database what you wanted, and you don't tell it how you want it. And that's it used to be before SQL was invented. You'd have to tell the database exactly how to get to the result. Nowadays, we don't do that for a simple reason that the database always knows better than you do, because it has much more information than you have available. So that's the idea with streams, that we want to be able to do computations in a high-level way and have a complex library, then figure out how to do the kinds of optimizations that make sense in a particular situation. So as you can see here, lambdas are really essential for doing that. When we tell a stream, throw away a bunch of stuff, we have to give a concise way of describing what a bunch of stuff is, and we do that here with the lambda expression. Contrast that with the traditional loop code that you see up here. Over here, the condition was intertwined with, in an if statement, it was intertwined with policy on how you visit these elements, in this case, to use a linear iterator. If we wanted to separate that, if we want to say some pieces of behavior need to be given, but it should be up to the implementation to call upon them as needed, you really need to have an easy and concise way of specifying behavior. And that's what Lambda expressions are for. So a few facts about streams so that you can build up some intuition. So a stream is not a collection. When you see stream of string, it looks like it's the same as a list of string or in C++ a vector of string, but it's not. A stream does not store its own data. The data do have to be stored somewhere. In the streams that we're going to be using right now, the data will always come from either an actual collection or a file, but they could come from a database or from somewhere else from the internet. So there's nothing in the stream that says where the data need to be stored. Streams were, of course, designed to work well with Lambda expressions, just like I already said. Filter here takes, well, it really takes a predicate, but it's designed to have that predicate served as a Lambda expression. Streams are immutable. Unlike collections, the Java collections library is designed for mutable collections. You have like a linked list, and you can add something to it. You can remove things. You can mutate it in a number of ways. Mutation is not so great because it makes it very hard to parallelize operations on a collection. If you have multiple threads that all try to mutate a collection at the same time, you have to be. It can be done, but you have to be very careful about it. So streams take a more modern approach and say a stream is immutable. If you call any method on it, you just get a new stream. So, for example, when you call stream.filter, you get a new stream that is just like the old stream, except all of the elements that don't pass the filter are not in there. Now, remember, streams don't store their data. So it's not that the data actually had to be shoveled over in any particular way. It's entirely up to the stream on how it manages the filtering process. Maybe it keeps a list of the positions of the things that are not there. Actually, as you'll see later, it's much more sophisticated than that. So, but all stream methods produce either new streams or non-stream results, such as count over here. It produces a counter. Note, by the way, the counter is a long, because the idea is that the overhead of stream processing makes most sense when streams are large. Stream processing is lazy. And so the idea of streams is to do as little work as possible. In the previous example, that wasn't particularly apparent. To count all of the long words, you have to find out what the long words are and then count them. There's not much opportunity for laziness. But let's look at a different way of operating on a stream. The limit method will take a stream and limit its size to whatever the argument is. So here we say we're only interested in the first 5 long words. If there are more than 5, just throw away the others, or just don't show them to us. It doesn't have to actively throw them away. They just are no longer there. If there never were that many, then it's just shorter than 5. So limit is the maximum. The 5 here is the maximum size. So now how can you implement limit? If you did this the traditional way, think about how you would have done that in inf1 or in AST1. You would have taken your list of stuff. You would have then filtered out those that don't match. And then you would have thrown everything away that was longer than 5. But that's really wasteful. And that's not how stream operates. So streams are they try to be very smart about this and to be very lazy. So when you call limit 5, actually nothing happens. So far, the stream operation here just sits there. But at some point, I will want to do something with the resulting stream. I might want to convert it back into a list, or I might want to call count on it or something. At some point, it has to start doing work. And the very first thing it's going to say, okay, fine. One needs to have the first element of the stream. So the limit 5 at this point says, fine, we'll have to go one layer further down. We'll have to call filter to get an element. filter will not compute all elements. It'll just run until it finds one element that passes the filter. And then that element will be returned as the first one. Then when the second one comes around, the same thing happens. So filter will look at more elements and deliver one. At some point, maybe someone will say, well, what's the sixth element? At that point, limit 5 will say there is no sixth. No more filtering will happen. And so filter might have, so we don't quite know how many elements of the stream were actually looked at, because we don't know how often the filter succeeded. But we know that after it has found 5 elements of length 10, nothing beyond that is looked at. So the stream here could be large. It could in fact be infinite. We will soon see some infinite streams. You can think of the streams of all numbers. And that's just fine, because for any evaluation, one only needs a finite number of elements. So the entire idea of streams is to make it so that they're done lazily. So as you can imagine, the implementation of streams is incredibly complex. Of course, we never look at it. As users, we just take advantage that someone has figured all of this stuff out. Just like when you use SQL, you never worry what happens when a select actually is executed. Right? I mean, there's some query optimizer that then kicks in and stuff. And we never care about that.
But
What?
internally, if they get the stream on the list, how does it store the...
Well, every stream, as we'll see in just a minute, will come from some data. And so if you make a list into a stream, then eventually it'll have to go into the list. And so at that point, a stream that's derived from a list will have an iterator floating around somewhere. It'll have some internal state, but that state is invisible to the user. All right. So up to now, the interactive part of the course was that you would do some code check questions. So I want to do another set of questions where you get a turn. And these ones, normally the way I do them is the students either have a hardware device where with 4 buttons, A, B, C, and D, or there's a little program that they run where they click on which of these answers is good for them. That has the advantage everyone votes anonymously, there's no embarrassment, and at the end we know whether students understood the stuff or not. Right now we're going to do the low-tech approach. So if each of you could please pick 4 cards, A, B, C, and D. And the rules are that you so just take one of each and turn it around. The rule is you read the question, you come up with your answer, and only when I say hold up the card, you hold up exactly one of the 4 cards. So that way you then can't get influenced by the votes of anyone else. There's no penalty for a wrong guess. So the rationale for doing this is I want to know whether you have a clue of what I was just talking about. Frankly speaking, there's another rationale. Sometimes I want to show you that you don't have a clue of what I was just talking about. And so sometimes I design these questions, or I try to design these questions, so that I get an equal mixture of A, B, C's, and D's as the best result. And when I do that, then I'm really proud of myself. Sometimes I think I manage to confuse everyone and I fail. So we'll see how this one goes. So in this particular question, I'm giving you 2 pieces of code. The first one up here, and the second one down here. And they're supposed to do something. They're supposed to give you a true if the stream has at least 10 strings with 3 letters, and a false otherwise. Maybe one of them doesn't work. Maybe both of them work, but one of them is more efficient. And so I want you to figure out which answer, A, B, C, or D, best describes the correct answer. And I fully realize that when I ask about efficiency, you don't really know. So all I'm after is your best guess. So it looks like everyone has an A, B, C, and D card. So I will count down to 0, and at 0, please hold up the card that you think reflects your answer. Okay. 10. Does anyone not have their cards? We want to make sure everyone. Okay, you only get to hold up one card. One and only one. Yeah. What happens to someone who holds up no card? Then they will have to explain their indecision in front of everyone else. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. So we have a almost universal answer for C and a couple of yeah, that's okay. So almost everyone said C, saying that the first one is more efficient. So that's good. So that means that actually just about everyone understood what I was just talking about. So yes, they both do the same thing. The thing that's wrong with the second algorithm is that the second algorithm will first find all of the strings, even though there might be millions, and then count them. Whereas the first one here will stop filtering after it has found 10 answers. Now, the count might, of course, be less than 10 if there were not 10 matches. So if it's equal to 10, then that means we had at least 10. So yes, so everyone got that. Almost everyone. That's great. So if for whatever reason you didn't and have a question, this would be a good time to ask it. Like, why didn't you think B would work? Because I think one of you said it was only A. And,
because I was not understood the question.
Okay.
Le truc, c'est que l'unité, ça peut rendre moins.
Yeah. I think the structure of the question was, yeah. So it'll get better when we have more of those. All right, so more into the business of streams. How do we make a stream? There are several ways of doing it. If you, for whatever reason, just want to make a very short stream, which happens mostly for examples and for oddball situations, use stream.auth, and it gets some number of alternatives, and then it makes a stream of whatever type you have in there. So here I've made a stream of string or a stream of integer by just giving the elements to stream.auth. So that's a finite, normally short stream. It also works for arrays, and then it could be long. So if I had an array, and we'll later see some situations where the arrays are quite long, and then I call stream.auth the array, and again I get a stream backed by those elements. More interestingly, any collection of the Java collections library can be turned into a stream. So as of Java 8, a new method has been added to collection, namely .stream, and it gives you a stream backed by that collection. So this could be a list, an array list, a hash set, whatever one of those collections you have, you can instantly get a stream by saying .stream. And so this was done on purpose, so that you should be encouraged to, whenever possible, use streams if you need to get some data out of a collection. So from now on, whenever you use an iterator, you should feel slightly ashamed and ask yourself, can't I use a stream instead? Or, God forbid, a for loop. No one uses a for loop anymore, right? That's so last millennium. So nowadays, try to use streams. There are also a number of nifty utility methods that yield streams, and my absolute favorite is files.lines. So if you want to read in a file, a line at a time, in the olden days you might have used a while loop and used either a buffered reader or a scanner, and so that, again, that's so old-fashioned. Nowadays, you just get a path to the file, you call files.lines, and you get a stream of all of the lines that you can then work through. it is considered a good idea to put this one into a try with resources block. So you say try, then you put the declaration of the stream in here. And this is a Java 7 construct that I don't know if you ever ran into it. The way it works is that at the end of the try block, the underlying file from which the lines are read is automatically closed. And that's something that you will want in a larger program. I mean, for a small student program, it doesn't make a difference. But in a large program, you generally want to close files that you open. So this is automatic, almost like a destructor would work in C++. Now, for fun, you can make infinite streams. The iterate method does that. So iterate takes a seed value and a function that produces the next value out of the previous one. So what you see over here is the stream of all integers. Almost, right? It's all integers mod integer dot max and or whatever the max value, that's what it is. So if I use big numbers instead of using 0, if I use new big number of 0, then I could truly make an infinite stream of all big numbers. You might say, well, how does it fit into my poor little laptop? And of course, it is never fully evaluated. If you were to try to turn that into a collection and print out all the elements, then something bad would happen. But at some point, you will limit it, and then an infinite stream is not a problem. As we'll see next week, it's often beneficial to take any old stream and turn it into a parallel stream with a parallel operation. And at that point, the same user interface applies. You can still call filter and count and all of those nice things, but they're automatically parallelized. So you may have had a course somewhere. Do you have a course somewhere where you learn how to use like semaphores and locks and those things? And so no one does the same, right? So that's so last millennium. So so you call parallel, and you rely on someone who's smarter than you and me to have implemented those locks correctly. Because as you know from having taken that course where you use locks, you always did it wrong, right? If you have not learned that, you need to retake that course. There's only one lesson that you learned from a basic course in concurrency, namely that is that you never ever want to do this. Concurrency is too hard for the average user. And well, maybe that's what we should do next Friday, and then I get that point across. All right, so now it's your turn. Make me a couple of streams. So for a given sentence, or really string, of word, whatever, make me a stream of all strings of length 1 in it. And then make me a stream that consists of star, 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 and so on. So here's the code check thing. It's down here. To do the first one, you have to know a little trick. You have to know that when you have a string and you call split with an empty string on it, then what you get back is an array of the strings of length 1 in it. So for example, when I take the string hello, and I call split with an empty string on it, then I get an array of 5 strings H, E, L, L, and O. Just as an aside, let me show you a little code check trick. If you want to know what the expected answer is, you can type in any old answer that compiles. Like here, I need a stream of strings, so I'm just giving it a couple. And then you can submit. And then, of course, it tells you that you are wrong, but whatever. Then, but at least you see what it is that you were expected to deliver. So as another clue for the first one, stream.auth works for an array. And I told you how to make an array. Out of the word. And so that solves the first part. But how do I make that infinite stream?
Stream.iterate.
Yes, so there's only one way that I've shown you how to do that, and that is stream.iterate. Oh, I'm just going to copy this here and then fix it up. Okay, now of course in this case here I don't start with 0. So maybe I start with the empty string. And then I don't say +1, but plus an asterisk, right? See what I get? Oh, okay, because I didn't put a semicolon. Okay, what did I do wrong? The red says I must have been wrong, right?
Start with a star.
So I should have started with the star. That's what it expected it to. So that's easy enough. Right, so we start with the star. And now everything is green, and so all right. So you see how to make some of these streams. So you know how to make them. You know a couple of ways of transforming a stream, such as filter. And so generally the life cycle of a stream is you make it, you transform it, transform it, transform it, transform it, and when you're all done, you need to harvest the results. And there are several methods for getting results, and we're getting started with a few of them, and as we go along, we'll learn more. There's count that gives you a single value. For some streams, as we'll learn later, you can call sum and then get the sum of all of the values, but those have to be streams of numbers. Quite often, we will take the stream and turn it back into a collection. Because with a stream, there's no way of looking at individual values. It has no API for that. So when you're all done, it's perfectly legitimate to move it back into a collection and look at the elements the way you have it. So there's two ways of doing that. The first one is you can collect it your results into an array. That you do that with the toArray method. The toArray method is a little nasty in that you have to give it an array constructor. It cannot infer that. We talked about that briefly last Friday. And so you just have to remember when you use toArray on a stream that afterwards you give it a whatever the type was, brackets, colon, colon, new. I find that so unpleasant that I almost never do that. The other thing that is much more common is to collect a stream back in a traditional Java collection instance. And there is a general method called collect that allows you to do that. So collect will return some collection. What kind of collection? There is a parameter here of type collector that you never actually produce yourself because there's a bunch of factory methods to give you appropriate collectors. If you call collectors to list, you get a collector, whatever that may be, that can produce a list. You call collectors to set, then you get a collector that puts stuff into a set. And those are the two most common ones that you're going to encounter. So when you do that, then you get this. Why didn't they make a to list and a to set? They just wanted to keep the API as simple and general as possible. And it's a bit of a pain because these are so common, but that's the way it is. A third one that is very occasionally useful is if you call collectors.joining, then, and this only works for streams of strings, then they're all joined together with that separator, in this case, the comma. What if you don't have a stream of strings? Does it call toString on each of them? No, it doesn't, for reasons unknown to man. So the reality is that as long as you remember collectors to list and collectors to set, then you're all set. And so just to see whether you figured this out, there is another program for you to do. And this is a very realistic kind of thing that you might be called upon to do. So you're given a collection of strings. And let's see how the exact wording is. So you're supposed to find the first n strings in there that have length at most max length. Once you've found n of them, you're supposed to turn the result into a set. That set might actually have fewer than n elements if there were some duplicates, and we're okay with that. And you're supposed to use streams. In fact, you could try, what if you say, I don't want to use streams. Then code check says, don't use a for loop. So,
What about the collect method one?
What's a collector?
Collectors to
The collector's tool list gives a collector.
collectors to that's generated.
It generates a collector. Yeah. And a collector has something to initialize and update to take the result or something. Yeah. If I recall correctly, that's the trouble with a collector is if you have a parallel collection, then it needs to be assembled in order. That I don't know whether the collector, I have to look at the details.
Ah, voilà.
That would be bad.
Totalement
Yes. Yes, your keyboard is on down to
C'est un bordel. La merde.
so it's undefined. So you're not supposed to do.
C'est quoi la taille?
I mean, if it's just a regular list and you have a reference to it, then that's true in any context. Yeah, so in the time that you call stream on it to the point that you're done. It would be a really good idea not to. It doesn't make any sense because the collection in general have no way of
Devant le grenier là.
so otherwise they would have to have an extra flag and have a mutator to check against that flag. And not just that, they would have to check against that flag.
Au moins, le sujet généré, ça va pas donner.
You know, I think with the linked list, they could have done it just like the concurrent modification exception.
All right, so there's three things one has to be able to do. You have to take a collection and turn it into a stream. Well, that is very easy. You just say dot stream. Then we want to do something with it. We want to filter out strings. I don't yet know which, so right now we'll just leave them all. Then we are only interested in the first n of them. And then we want to turn them into a set. So collectors dot, what was it, toSet? Just want everyone to see where. So it's right here. And we want to return this. All right, so I guess we should focus on what goes on here. So we only want to have the ones that are at most max length. And I think that's it. Yeah, all right. So if you had programmed this the old-fashioned way with loops, what would you have had to do? You would have said, fine, I'll have a set of string result equals new hash set. You would have to have a counter. You would have to say yet have to have an iterator, right? Or we can use it an enhanced for loop, so we can say string s in strings if s dot length at most max length. Then what do? We put it into the result. Add dot s. Oh, I guess I also have to increment the counter, right? Because I should only want to do this 20 times. Count plus plus. And at the end, I'm returning the result. Okay, what did I do wrong? Never mind the fact that I already have way more lines than I had with the streams, right? But it's also wrong. What's the mistake?
Going to which is n, you have to build a for.
Okay. I can't do that, right? Okay, at this point, I'm ready to cry, right? Because now I have to change the for loop into a while loop. I have to have an explicit iterator. Or I guess I could say inside here, I could have another, I could return in here, right?
You could just have a break.
I could have a break, but I'd rather die than have a break.
Why?
So I never use a break. I have sworn to my mother, said, "Mother, I may become a programmer, but I promise you one thing, I shall never use a break." And she let me go. So no go to, no continue, no, yeah, no labeled break. So you see that so seriously, right? You start out in some way, and this is something that happened to you all the time when you did what, not how. You had to then change your strategy as you went along, and it's actually tedious to program. With streams, life is easy. You just say what you want to achieve, and once you get the hang of how to apply these things, it is shorter, it is easier to read, and when these collections get large, you give the library an opportunity to do the kinds of optimizations that would be really hard for you to do.
Is there a sort function?
Yes. So we'll see many more of these today and tomorrow. And yes, you can sort streams. You can say throw away duplicates. So there's a good number of useful utilities on these things. There's not everything there yet, and so undoubtedly in Java 9 and 10 this library will get better. But there's already there's a lot of stuff that once you get your mind into working with the streams rather than against them, where you can just get just about every result that you want. So just a little tip, it's a good idea to write up your calls as a pipeline with one operation per line. So here you make the stream in the first line, then you apply a single operation and a single operation, and in the end you end up with a operation that gives you a non-stream result. And that way it's easier to read. If you try to cram everything into one long line, then it doesn't even fit on the slide. All right, couple of important transformations. The single most important transformation is map. So map will apply a function to a stream, give you a new stream that consists of the map applied to everything. So here's the single simplest example you could imagine. I have a stream of strings, and now I want to make all of those strings into lowercase for whatever reason. And so I apply the lowercase. I could simply write string colon lowercase as well. I apply this lambda expression, and then I get a new stream that contains these all. Now, in reality, of course, it's not that all of the elements are being processed. Remember, stream processing works backwards. And all that's going to happen is if one of those elements is needed and it is determined that it must come from whatever preceded the map, then the previous element is fetched, the function is applied, and the result is then further processed. So here's another example where, for whatever reason, I have my lowercase words and I want to remove all vowels from each of the words. So I apply this function here, which removes all vowels, and I'm left over with a stream that only contains consonants. Now I might want to have the length of each of these elements, and so now I have this consonants only map and apply the length, and then I get a stream that contains these lengths. So if my job was to read in words and to find out how many consonants each of the words has, this would be one way of doing it. I can say map, map, map. I could use a single map and combine the operations. In terms of efficiency, it doesn't make that much of a difference in the end. Of course, it's slightly more efficient to put a single map, but you should do it in a way that makes it easy to do. So truth be told, the way that I usually develop this kind of stuff is I transform the stream into something. Oftentimes, I transform, filter, or sort, or do some other things. And so one does these operations a step at a time until one gets closer and closer to the actual result. So
Can you join streams like in
No.
SQL?
no, you can. There's no theoretical reason why you shouldn't be able to zip them together or something, but the implementers ran out of time. So typically, in a like in Scala, you can take two streams and interleave them, for example, which would be useful. There's the kind of SQL join that you're asking. You can do with grouping. We'll see that next week.
Is there a group?
Yeah, there's a group by. Group by is the killer
No.
stream feature. Yes, absolutely.
But,
Yes.
But there's no zip, right?
There's no what? There's no zip.
Okay.
There's unfortunately no zip. There are many times that I would love to have a zip or a zip with index, and that's just a question of time. There was a prototype version of that in Java 8 as it was in development, and then they ran into some issues with parallelization with it, and then they took it out again. But there's no theoretical reason why it can't be done. They just have to work harder at it. So undoubtedly we will get that stuff. There's also a flat map that I haven't gotten around to describing, and I may if we have extra time. All right, so here's another clicker question. So I want to know which of these two yields a stream of all words that starts with an A or A. And if both of them do, and I don't recall anymore if both of them do in this case, which one of them is more efficient? All right, is everyone ready? Okay, go. Okay, so we have, everyone's pretty much said C or D. More people said C than D. And I don't actually know the answer. So both of them work, right? So here we filter out the A's and A's, and here we turn them to lowercase. Here we first turn them to lowercase, and then we only need to look for the A. So why would the first one be more efficient? Most of you said the first one's more efficient. What's better? Yeah. There are fewer elements that need to be lowercased.
Because you're turning to lowercase on the first letter before. Not all.
Yes. So in the second one, remember that we work backwards, right? So let's suppose we want to take 100 elements off this thing. So in that case, we're filtering. So we need to apply the lowercase map to sufficiently to sufficiently many elements so that we can make this decision. Which will be more than 100, because some of them will not start with an A. Once we found 100, we never apply lowercase again. Okay, why is that any different from here? It'll do this pretty much the same thing, right? Wouldn't it?
I'm not sure to understand in which order are the filter and the map executed.
They are executed. You can't even tell at this point. So at this point here, when I just have this, what gets executed? No.
No?
Nothing gets executed so far.
Okay.
Right? I still have a stream. Right? Nothing gets executed. So there's absolutely no difference up to this point. So if anyone would have said, this is bogus, I can't possibly give a distinction between C and D, that would be the best answer, right? There's no difference. At this point, it piles up these two operations to be done later, and this one here piles up these two operations to be done later.
That's when you check, get one result.
Yeah. Once I get a result, then this might become an interesting question. So this is another beauty of the clicker questions, that it can be that none of them is entirely right. So, but in general, in this case, I would say the difference in work is negligible. I would not start worrying about which of these has a higher workload, which was my point of this question. All right. So,
Getting back to database, it's better to filter first and then you start.
in general, one would think that it's better to filter first, but to extract a substring and then call, that's work. Yeah. In general, I think the rationale is that it's probably better to filter first. Yeah. So a few more useful transformations, and that'll be all for the day. You've seen filter. There's the opposite of what was the other one called? I can't even remember. The opposite of limit, which is called skip. Oh, it probably does say here. Yeah, here we have limit, here we have skip. So skip discards the first 100. There's distinct. Distinct is very useful. It yields a stream with all the duplicates removed. There's sorted, which yields a stream with all the elements unsorted. Now, as you can imagine, sorting is expensive. So when you call sorted, nothing saves you from the fact that that is expensive. What happens if you apply sorted to an infinite stream? You will not live to see the result, right? Because it has no way of knowing what that stream is, so it would keep on going. So distinct, on the other hand, you could use on an infinite stream. The way that distinct works is it keeps a set. It tosses every element that it's ever seen into that set, and if it finds that it has already seen an element, then it skips it. So it's kind of like a filter where that set is built into the filtering. So you could perfectly well filter you could perfectly well use distinct on an infinite stream. So one other common error is we've seen a bunch of these operations that operate on a stream and give you a result, such as count and collect. Once you use one of these so-called terminal operations, then the stream is used up and you can't use it again. So over here, for example, where for whatever reason I have a stream of something, then I limit it, and then I call collect. At this point, this stream here, I cannot do anything anymore. If I try to apply another stream operation on it, like skip, it doesn't work. So that's actually a bit of a pain. What if you want to have the first 50 elements, then the next 50, then the next 50? There's no natural way of doing that with streams. That's not how streams work. There is a way of doing it later with grouping that we'll see, but it's a little awkward. So, and there should be a way of doing it, and in the Scala streams, of course, there is a better way of doing it, but it's the fundamental limitation of streams that they follow a very simple life cycle. You make the stream, you apply transformations on it, you apply a single terminal operation on it, and then the stream is dead and gone. And so the way to to avoid this error is to use this pipeline notation. If you always use this form, then you have no reference to the stream. That's the best thing. If you never have a reference to the stream, then you're never tempted to use it after it no longer exists. So in the example that I had, you have to use two streams. And that's fine. Sometimes that happens. There's no shame in using two streams. You just make a stream and then you make the stream again. All right, so now a bunch of exercises. The first one is actually kind of interesting. So here what I want you to do is take a word and tell me how many distinct vowels it has using streams. Now you already know how to take a word and turn it into an array of individual characters. Then you can call dot stream, and that gives you a stream of the individual characters. And then you can call filter and do something like this. And that way you can retain only the vowels. What about accents? I guess you could put in more letters in here, right? A, umlaut, E with accent aigu, accent grave, and so on. But that's no fun. The better way of removing accents is to use Unicode normalization form D, as I'm sure you all know. Does anyone have a clue what normalization form D is?
Why D?
D for decomposition. So it takes a character such as an E with an accent, and it turns it into an E followed by an accent dead key. And it does that systematically. So if you have a German A umlaut, then it turns it into an A followed by the umlaut. So this is what's called normalization form D. And when you do that, then you can just take the first character, and that gives you the thing without the accent.
There's a way to strip out the accent.
This is the way to strip out the accents. Yes.
You don't want to have the second character.
That's right. So you just so what you do is remember what we have after we turned this thing into a stream. We have a stream of strings, each of which has length 1. Then you apply this magic method, and at this point here, you might have a string that has length 1 or 2. If it happened to have an accent, then the accent becomes the second one, and after that again has length 1. Now you just have to remember how do you apply a method to everything on a stream, and there's a slide for that. So the second one is a useful application of this. I'm giving you a file, I believe, of all words in the French language, and it gives you a list of all of them that have 5 distinct vowels. You've always wanted to know this, of course. Yeah. So now you are. And the third one is a little harder because I didn't know whether I would have more time or not enough time.
Est-ce que tout le monde a rendu les exercices de la semaine dernière? Non. Parce que... Hein?
You could use it as a filter, but that's not what I would do. So my philosophy is that I do things one step at a time. So I have a bunch of characters, and I want to remove the accents. That to me is a step. After I then remove the accents, then I can move it. You could combine both. You could put the removing the accent into the code of the program. But I like this idea of saying one step at a time.
Right, that is the shape. So one thing that's a little awkward when you program with streams is that you don't get an intermediate data structure that you can view. So one way of incrementally getting better is that you just accept that you're going to do the wrong thing at first. So over here, I'm just going to start out counting all letters. And then, of course, the counts are going to be wrong, right? This one's going to count 11 letters. But I can say, fine. Now I can get better by... Okay, now I have to remember my syntax. And so now I'm getting 4 vowels here. That's already getting pretty good, right? Here I'm getting by sheer dumb accident the right answer. But for a minute here, humor me. How can I simplify this expression? So this expression here, how can I make it simpler? Maybe I could use an L instead of an S. Is that a simpler letter? Can I do without the S? What's that? So here we have a method expression. Right, this is the contains method applied to this string. And so where's the parameter? Well, so that's the same thing as saying S arrow and then putting the S in here. Right, so that seems well worth it. So, and by the way, someone was asking me before, should I first strip off the accents and then filter? Or should I, in the filter, strip out the accents? And so my feeling is you should always do things a step at a time. So I would first strip off the accents. And then filter. Because otherwise I would never have had the satisfaction of writing it in this compact form. And that, after all, is what programming is all about. So here I'm getting quite close, but why am I having 4? Well, it's called distinct vowels. Apparently I'm not throwing away the duplicates. So you can figure out how to do that.